When we talk about artificial intelligence today, it's often framed as an omniscient, magical robot brain, a conscious entity quietly observing us from the cloud. We interact with these systems constantly, reading emails written in seconds or scrolling past photorealistic images conjured from a single sentence. Because we only ever see the finished product, it is easy to assume the machine is thinking rather than calculating. Stripping away the sleek interface reveals an engineered architecture. Think of it like a master chef operating an industrial kitchen. To get a perfect final dish, the chef needs massive raw ingredients, a highly methodical processing recipe, and rigorous continuous testing. Let's step inside that kitchen. By observing how it's built from the ground up, we can see the mathematical mechanics behind the illusion of thought. Every AI begins its life in a complete vacuum. You cannot hand a computer a dictionary definition of an object and expect it to understand the concept. Instead of human logic, the system requires an avalanche of raw data, millions of disconnected pieces of information poured into the system at once. We call this raw material training data. If the goal is to build an AI that can recognize a cat, the system must process millions of individual photographs of cats, dogs, and birds. The scale of this ingestion pipeline is extreme. A human toddler can learn to identify an animal after seeing 1 or 2 examples. The machine requires 10 million. Yet throwing a mountain of raw data into a hard drive is meaningless noise on its own. To extract value, the system needs an intricate architectural framework to find the patterns. This brings us to the core of the architecture, the neural network. This is the chef's brain, designed to organize those chaotic ingredients. The network handles complex recognition problems by slicing them down into tiny, isolated mathematical steps. This diagram illustrates how data filters. Raw data enters left, where the first layer isolates simple straight lines and circles. Flowing into hidden layers, these isolated shapes connect, synthesizing into structural patterns like triangles mimicking cat ears. The final layer aggregates these fragments, calculating the probability that this arrangement is a cat. This sequence of hierarchical pattern matching algorithms mimics the appearance of intuition through nothing more than layered math. There is a catch to this architecture. Upon its very first activation, the network's guesses are almost entirely wrong. It will look at a cat and declare it a chicken. This initiates the taste test. A mathematical supervisor, a metric called a loss function, flags the error, calculating the exact distance between the network's wrong guess and the right answer. Once flagged, the system executes backpropagation. The network travels backward through its layers, adjusting internal dials, known as weights, to correct the specific mistake. This grueling process repeats this precise mistake and fix loop billions of times to reach useful accuracy. The perceived intelligence of an AI is the exhaustion of failure. The machine arrives at perfection because it has systematically made and corrected every possible mistake. When we zoom out, we see the entire assembled architecture working in unison: the data input, the neural network layers, the final output, and the feedback loop. The chaotic noise of millions of raw images has been refined into a synchronized mathematical engine. This architecture is a transparent, relentless feat of structural engineering. The system digests millions of isolated data points from the past to practice making accurate predictions about the future. Demystifying these mechanics replaces the fear of a ghost in the machine with a clear understanding of the massive, iterative labor required to make a computer see.